Hello everyone, welcome to today's video. Today we will be covering graphs of polar equations. So in our last video we looked at polar coordinates and this new polar coordinate system, and we talked about how to convert Cartesian equations to polar equations, and today we're going to be putting all those skills to use, and we're going to look at some graphs of polar equations. Now the point of this section isn't so much to do a deep dive into these graphs, but to just get a sense of the overall shapes and what the equations or formulas look like that produce those shapes. So we're going to graph some polar equations by plotting some points, and then we'll look at some different formulas for some different shapes we'll see. So we got circles, which we're familiar with, and then we'll learn about cardioids, one loop limaçons, inner loop limaçons, lemniscates or lemniscates, depending on who pronounces that, and then we'll look at some rose curves as well. So the first thing I just want to show you here is just a general overlook of all the shapes that we're going to see before we just start plotting points and it looks just like kind of a hodgepodge of dots all over the place. These are just the general shapes we're going to see. So like I said, we know what a circle looks like. We've got these cardioids here. We've got these two types of limaçons. So either there's one loop or there's two loops there with an inner loop. Lemniscates kind of look like infinity symbols, and then we've got these rose curves here. So we'll see this again at the end, but we're going to go through all the details here and see what's what. So first we're just going to look at graphing some polar equations by plotting points. We'll do this a bunch of different times with formulas that are equations that look somewhat different. So here we just have that r equals 3. So what we're asked to do here is just make a table of values here, meaning maybe I'll remind you that what this says is that r is a function of theta is going to be 3. So maybe thinking about it like this, when we plug in some value of theta, so we're going to take some angle here and rotate around this grid, and we want to know what the radius is at that angle theta. So this is super straightforward since we just have a constant here. This is saying if I go to my angle of 0, so I'm looking at not rotating at all, where do I plot a point? I plot it at 3. So we'll go 0, 1, 2, 3, there's a point there. And if I rotate to pi over 6, well, that will also give me 3. So there's a 3, or we'll plot a point there. And at pi over 3, well, that's also going to give me a radius of 3. Maybe you see the pattern going on here. At pi over 2, we'll have a radius of 3, and that's going to be true at any theta that I put in here. So just kind of filling in all the dots here, and what do we get? We just get this nice circle here. So let me just connect all of my dots. We'll let the computer snap that in place for us. And there is our graph for this one. So if we just have this constant function, it's just giving us a circle with a center right at the origin here, right at the pole. So just wanted to quickly talk about that one before we get into some that are slightly more complicated here. So next we're going to graph something that looks like 2 sine of theta. So radius equals 2 sine of theta. So here we're asked to find the zeros, meaning where is the radius going to be equal 0. So that's going to tell us where it goes through the pole. So that is why we would want to know what the 0 is. It'll tell us where it goes through the pole. We'll look for the maximum radius value. So another good thing to know about these shapes is what's the farthest point away from the pole. And that'll help us in determining the shapes of these graphs. And we'll find any polar intercepts. So the polar intercepts are what go through the polar axis. So the polar axis is what we would typically call the x-axis. So just having those bits of information will help, and then we'll make a table to find the other values here. Taking a look at this one, first we'll look for the zeros. So this will tell us where it crosses the pole. Oops, not grosses, but crosses the pole. So it goes through the origin here. So we want to know where 2 sine of theta is equal to 0. That will give us a radius distance of 0, which means that it's just at the pole here. We'll divide both sides by 2 when we're looking at where sine of theta is equal to 0. Looking at an inverse sine, we would know that that is theta equal to 0 or pi. So as we plug in values here for theta, we will see that at 0 and at pi, we will be going through our pole here. Let's look for our maximum value. And this just gives us a max distance from the pole, just another nice point to have. And this happens when the sine of theta is at its max value. Since that is the thing that is changing, the part of the function that is changing is the sine of theta, we want to know when sine of theta is at its max. Well, that's going to be when sine of theta is equal to positive 1. And that's going to be when theta is equal to pi over 2. And technically, any revolution of pi over 2. So we'll write that in there. For this one, we might leave some of this plus 2 pi k, or get all the revolutions out of there if we need to. But that's what we get here. So now if I plug theta equals pi over 2 into my function, this will tell us what the max value is. So doing this kind of pre-work here gets us the theta value that will give us the max, and now we'll plug it in to our formula. So we're looking at r of pi over 2. Remember that r is a function of theta. And we'll get 2 times the sine of pi over 2, which we know is just 1. That's what we figured here. So we get 2. We get that the farthest distance here is going to be 2. So we know at 0 and pi, we're going to have a point at 0, and we know at pi over 2, we're going to be a distance away of 2. So we get these points here, but we're missing a lot of other points here. 2 points is not going to get us a general shape. So we're going to go plug in some other points here, and we might not always plug in exactly the same points, but right now we're just trying to learn some general shapes here. So the points we're going to plug in here are 0. We know that that is going to be going through 0. That's a radius length of 0. That's what we found right here. And then we'll look at pi over 6. We'll look at pi over 3. We will look at pi over 2. We will look at 2 pi over 3. We will look at 5 pi over 6. And we will look at pi. And we know some of these. We found that at pi we'll be back to 0. And we know at pi over 2 will be at 2. So those values I get just from the work that we have done before here. To get the other values here, we just need to plug things into a calculator. So you'll just literally plug in to get this value 2 times the sine of pi over 6. And we'll get that that is 1, since the sine of pi over 6 is 1/2. And then if we plug in pi over 3, we'll get this about 1.73. And then we'll have some symmetry on the other side. You'll actually notice a lot of symmetry as you're plotting points here. Values popping back and forth, maybe the negative versions, maybe they'll stay positive, or maybe the signs will stay the same. But now as I go through and plot these new points here, maybe I'll just do them in a different color just for fun. So at pi over 6, we're at 1. So I'm going to go a distance of 1, and then I'm going to rotate pi over 6. So we're going to have a point right there. I'm going to erase that line just because we don't want the line. But there, we're getting a point. We're getting another one at pi over 3. 1.73. So this is my pi over 3. I guess I could label some of these here. That's pi over 6. And at pi over 3, I want to be at 1.73. So I'm just approximating in, trying to get as close as I can there. There's a point. We've got pi over 2 being 2. At 2 pi over 3, we're going to be at 1.73 again. So that's around there. And at 5 pi over 6, we're back at 1. So that's what we're looking at. And now we can connect our dots. And what we're getting, I'll let the computer do the hard work here, is we should just be snapping to a circle. So we're getting a circle here with a diameter of 2. So this number in front, the a value here, as we will call it, is giving us a diameter of 2. So that is the farthest distance from the pole, or the farthest point from the pole is giving us the diameter of this circle. So there we go. If we have something of this form, a times sine of theta, or a times cosine of theta, we will end up getting a circle that crosses through the pole. So it'll be, well, actually, I'll just go to the next page here, and we'll see all of the different versions. So formulas for the equation of a circle. Some of the formulas that produce the graph of a circle. We saw one before, which is centered at the origin. These ones pass through the origin, or the pole. But some of the formulas that produce the graph of a circle in polar coordinates are given by either r a cosine theta, and you can see down here, for a being bigger than 0, you've got it on the x-axis, and this will be a common thing that we look at in trying to just get some general ideas of what these shapes look like. Cosine relates to the x-axis, so we're not too surprised that our circle here kind of lies on that x-axis with some symmetry there. And if a is less than 0, then it's still on the x-axis, it's just on the negative side. And same thing for sine. If we're looking at sine of theta, or a times sine of theta, and a is bigger than 0, then we know it's going to lie on the y-axis, which has some connection to sine. And if a is less than 0, then it will still lie on the y-axis, but in the negative direction. So hopefully you see some connections there between a being either positive or negative. And if we're looking at cosine, it will have some relationship to the x-axis. And if we're looking at sine, it'll have some connection to the y-axis here. So let's go ahead and take a look at this next example here. So here we still have 2. Now we switched to cosine of theta, but now we're adding 2 to it as well. So we might still maybe be predicting we're going to get some sort of a circular shape here, but let's just go ahead and do the same stuff that we did before. We'll look for some zeros, some maximum values, see if there's any polar intercept. So the polar intercept, again, is where it goes through the polar axis here. On this last example, the spot where the 0 here was the same as the polar intercept. So we were still also getting the polar intercept right here. I didn't point that out exactly when we did this last one, but it showed up as part of the problem, so we didn't need to do it separately. All right, so let's take a look at this guy here. Get rid of some of my squiggles. All right, so we'll look for the zeros. And this is going to be where r is equal to 0, so where the radius length is 0, and that's going to tell us where it's passing through the pole. So if I want to know where 2 plus 2 cosine theta equals 0, we'll set that up. We'll subtract 2 from both sides. We'll get 2 cosine theta equals negative 2. And if we divide both sides by 2, we will get that cosine theta equals negative 1. So we're looking for what angle, theta, would give us a cosine value of negative 1. And that is going to be pi. And technically any revolution of pi, so maybe I should write 2 pi k next to it, but we're just going to be focusing on just one revolution here as we're looking at this. We'll see that one revolution should complete our shape in most of the cases here. So this is telling us that we are looking at the point, or if I wanted to graph this point, it would be a radius of 0, and we're looking at pi here. So, it's hard to see what angle that is, but that's going to be where we're going through our pole. There's our 0. If we want to know the max value here, we're going to find the maximum when cosine of theta is equal to 1. That will give us the maximum value here. So when cosine is equal to 1, that's when theta is equal to 0. So we'll plug this value into our function. We have a function r of theta. We're plugging in 0 here, and we're going to get 2 plus cosine, I'm sorry, I need another 2 in there. 2 plus 2 cosine of 0, not theta, 0. And this is going to give us 4. So we know that if we don't rotate at all, 1, 2, 3, 4 will be out here. All right, now that we've got the 0 and the max value, we just have 2 points on the graph here, which isn't going to do a whole lot of good for us in terms of getting the overall shape. So we'll fill in the rest of the table that we've got up here. And these are just kind of some random-ish points. As we do some other examples, we'll perhaps look at more points, but I'm just trying to cut to the chase here. But what have we found so far? We know that for the zeros, that's going to be at pi. So we've got a 0 at pi. And at 0, we know it's going to be a radius of 4. So we get those 2 for free. Plugging the rest of these just into a calculator to get the other values here, we're going to get that at 3 pi over 4, we're looking at about 3.41. At pi over 2, we're going to have a radius distance of 2. At 2 pi over 3, we're going to have a radius distance of 1. And then we'll notice some symmetry going back the other way here. So we will get the rest of these points in green plotted in here. So at pi over 4, we're looking at about 3.41. So pi over 4 isn't on here, but maybe we can just kind of rough in a line here to represent pi over 4. And then we're looking at a radius distance of 3.41. So we'll count out 1, 2, 3, and just a little less than half. So we'll get another point there. At pi over 2, we're looking at a radius distance of 2. So there's a radius distance of 2 at pi over 2. At 2 pi over 3, we're looking at a radius distance of 1. So there's that. And then at pi is when we're coming back and we're hitting the pole. So I just kind of like to go through as we're going through either each quadrant or each half of the semicircle here, especially as we start to understand what these shapes look like, just to kind of connect some dots and see what we're looking at so far. And we're getting a shape that looks kind of like this start of a spiral here. So let's see if we keep spiraling, or what happens? So at 4 pi over 3, we're back at 1. So at 4 pi over 3, that's going to be here. So we're skipping 5 pi over 6 and 7 pi over 6. Those are going to be very small values, so we're skipping over those for here because I know what to expect so far. And then at 3 pi over 2, we're at 2. And then at 7 pi over 4, which again isn't on here, but it's going to be around-ish there, we're looking at about 1, 2, 3, and about 3.4 is about there. And so if we connect these dots, we'll get something that completes this shape here. Let me get rid of these guides just so we have a better look at the shape. Whoops. But there we go. Here we have our shape, and this is going to be called a cardioid. It kind of has this heart look to it, which is, I'm assuming, why it's called a cardioid. But yeah, let's take a look at the general versions here. So the formulas that produce the graph of a cardioid are given by r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta. So just kind of looking back here, we had some value in front of the cosine, or it could be a sine, and then we're adding some value in front of that. It could technically be behind, but this is just the standard version, the standard way to write these things. Here what we're noticing is that a and b are equal. So what we saw in this last one is that they were both 2. So when we have the coefficient in front of the trig, either sine or cosine, being the same as the coefficient in front, or the constant in front, then we get this cardioid shape where it kind of just pokes into the origin or into the pole here. So just the different versions here to look at for cosine. Again, for cosine, those are going to be related to the x-axis. Since cosine deals with the x-axis, we know that cosine of 0 gives us 1, and then we're going to multiply that by whatever this is, and then we're going to add some value to it here, and that's just going to stretch things out on the x-axis. Or similarly on the other side, if we have some negative value, it'll stretch it in the negative way. So hopefully there is a natural connection between cosine and the x-axis, and why these graphs kind of live on the x-axis here. And then similarly, let me erase some of my junk. For sine, we have these living on the y-axis. So if the b value has a positive in front of it, then it will live on the positive, mostly on the positive side. That's where the largest value will be, is on the positive side. Or if we have a negative in front of the b value, then it will be down in the negative direction. But sine is associated with the y-axis, or what we would typically call the y-axis, or we call it the sine axis maybe. And then cosine with what we would normally call the x-axis, or the polar axis that we call it here. So there we go. Those are cardioids. All right, so let's take a look at another example here. So what we notice on that last one is that the coefficient in front of the sine or cosine was the same as the number in front. So the a and b were the same. Here we have the a value being bigger than the b value. That's what we're, just making sure. Sometimes those variables get reversed. So here we have the a value being bigger than the b value. So a is bigger than b. So let's see what happens once we get into this situation. First thing that we'll do is look for our zeros. So we're going to set this equal to 0. 4 minus 3 sine of theta equals 0. We want to know what theta value would cause this graph to go through the pole. So if I subtract 4 from both sides, we'll get negative 3 sine of theta equals negative 4. And then we'll divide both sides by negative 3, and we'll get sine of theta equals 4/3, which is bigger than 1. So that means that there is no theta value that will do this. Theta is undefined, which means that there are no zeros. This graph, the shape of this graph, will not pass through the pole. It'll live kind of like that other circle did, entirely outside of the pole. So something interesting to notice there. Let's go ahead and see if there's any max values here. So far we have nothing to plot as preliminary points on our graph. But here we're going to see, and this is kind of something that you'll notice because you got to think about the signs here, but I'll just say out loud that here we're looking for the sine of theta to be equal to negative 1. things that we know about the shape of this graph, kind of based on maybe what we saw before, that since we have a sine, we'll expect this shape to kind of live on the sine, and since we're looking at a negative here, we might expect the maximum value to be kind of down there somewhere. So that's why we're looking for the sine value to be -1. There's some algebra there that you could justify it with as well. Or you'll just notice as you do more of these that this is what we want. So this will be when theta is equal to 3 pi over 2. So if we plug 3 pi over 2 into our function here, 4 minus 3 times sine of 3 pi over 2, we're going to get 4 minus 3 times -1, which is going to give us 7. So we know at 3 pi over 2 will be at 7. 1, 2, 3, 4, 5, 6, 7. Perfect. Just enough circles here to get that on there. And we know we don't go through the pole. So that's why we need a lot more values to plug into this one here, just to see where things land. But we do know so far that at 3 pi over 2, we're going to be at 7. So there we go. We will expect that value to come. And we'll find our polar intercepts as we do them on here. So the polar intercepts are going to be where theta is equal to 0 and where theta is equal to pi. So we will find them as we go through here either way. So I'm just going to start filling in the values here. But the way that we get these values is just by plugging them in to a calculator to find to find the value that goes with pi over 6. We're going to look at 4 minus 3 times sine of pi over 6, and we're going to get that that is about 2.5, or maybe exactly 2.5. Sine of pi over 6 is 1. Yeah, that gives us exactly 2.5. So as I'm plugging things in here, that's how we're getting that. If I plug in 0, we would get 4. Sine of 0 is 4. Is 0. Sine of 0 is 0. 4 minus 0 is 4. So just filling in some other values here for, oh, I'm looking at the wrong one. No, I'm not. I'm good. For pi over 3, we're getting about 1.4. For pi over 2, we're getting 1. For 2 pi over 3, we're getting 1.4. For 5 pi over 6, we're getting 2.5. And for pi, we're getting 4. So let's get these, since this is going to give us the top half of the graph here. Let's get these ones plotted in, and we'll see what we're looking at so far. So at 0, we're at 4. 1, 2, 3, 4. So 0, 4. Pi over 6, we're at 2.5. So there's 2.5. At pi over 4, I'm sorry, pi over 3, we're at 1.4. So that's about there. At pi over 2, we're at 1. So that's there. At 2 pi over 3, we're at 1.4. So we're back up around there. At 5 pi over 6, we're at 2.5, so 1, 2, 2.5. And then at pi, we're back at 4. 1, 2, 3, 4. So what this is looking like so far is going to be, have this little dimple here. So we'll actually end up calling this a dimpled something once we get there, but it's got this little dimple, and that's a nice smooth curve as it passes through that little dimpled spot there. So one thing to notice is on these cardioids, we get this cusp that it like really does kind of come in at a point and poke the pole there. Here we're getting a nice smooth curve that's going through that little dimple. So to get the rest of the values in here, maybe I'll just do these in a different color just to show the separation. 7 pi over 6, we're going to be at 5.5. Again, we're just plugging these values into a calculator and plugging them in to our formula over here. At 4 pi over 3, we would get 6.6. At 3 pi over 2, we know we get 7. We already did that one. And then we're going to see some symmetry on the other side. So 6.6, 5.5, and then at 2 pi, we're going to be back at 4. And hopefully that makes sense because 2 pi and 0 are the same. So what do we have here? 7 pi over 6, we're going to be at 5.5. So 1, 2, 3, 4, 5.5 is around there. At 4 pi over 3, we're at 6.6, which is like around there. We have some symmetry on the other side at 5 pi over 3. Oh, 6.6 is a little bit farther. 11 pi over 6 is going to be at 5.5, which is there. And then we're back at 4. So to finish this shape here, we're going to kind of just finish what kind of looks like the circular portion of this shape here, and we're getting something that looks like that. So that's all the same shape, even though I did it in 2 colors, but this is what we would call a one-loop limaçon. So you can see it's got this little like dimple in it. So let's take a look at the general properties of these one-loop limaçons. And it's got this weird spelling with, I don't even know what it's called. I probably should have looked it up, with the C with a little tail on it or whatever, but it gives it that pronunciation. So we're looking at one-looped limaçons here, and they have the same general shape of a plus or minus b cosine theta, a plus or minus b cosine theta, just like the cardioids did. But here we're seeing that the a value is bigger than the b value. Is that what I said? Yeah, a value is bigger than the b value. The a value is bigger than the b value. And it's also less than 2b. So you might notice on the other one that the a value was less than 6. And there's just a small difference here. That's going to be what we see in most of our examples, are these dimpled limaçons, where the a value is bigger than b but less than twice b. If a is bigger than or equal to 2b, we get something called a convex limaçon, and it looks the same, but the dimple isn't as pronounced. We just kind of end up getting this flat side. For these convex ones, you end up just kind of getting a flatter side. They start to look more and more circular as you go. But the dimpled ones are a little bit more interesting because they have a bit more of a shape to them. So those are mostly what we will see here. But there we go. Those are one-looped limaçons. So the same general formula equation. It just depends on the values of a and b. If a and b are the same, we get these dimpled, we get these cardioids with these cusps that poke into the pole. And if we are looking at one-looped limaçons, then the a value is bigger than the b value. The a value is bigger than the b value. And they have the same relationship of cosine corresponding to the x-axis, either in the positive or negative direction. And then for the sines, they live on the y-axis, either the positive or negative side. And by positive, and I mean that most of the graph lives on the positive side, or most of the graph lives on the negative side, or the max value lives on the positive or negative side. All right, let's take a look at this next example. So again, we have something of that same a plus b cosine theta, but now the a value is less than the b value. So let's see how this changes. What we're looking at here. So we'll see if we can find the zeros. The last time we tried to find zeros, we discovered that none existed. But we want to do 2 plus 5 cosine theta equals 0. So we're trying to figure out where this goes through the pole, and that would be where the radius has a length of 0. Subtract 2 from both sides, we'll get that 5 cosine theta equals negative 2. Divide both sides by 5, we'll get that cosine theta is equal to negative 2/5. Take the inverse cosine, and we'll get that theta is about 1.98, I believe, radians. Yeah. Which is not a common angle here. So we know that maybe as we're looking through these common angles, we might not see a 0 pop up, but one does exist, and it happens about 1.98 radians, which, let's see here, is going to be a little bit more than pi over 2. So somewhere between pi and pi, or somewhere between pi over 2 and pi, we should see this cross through the pole. All right, let's go ahead and see if we can't find the maximum value here. So looking for the max value, that is going to be where the cosine is at its maximum value, since we're adding everything together here. There's only positives. So this is going to be when cosine of theta equals 1. That should give us our maximum value. So that's going to be when theta is equal to 0. Plugging that into our formula here, r of 0 is going to give us 2 plus 5 cosine of 0, which should give us 7 again. So we're still getting this maximum value of 7. It occurs at 0 this time. So we can put that into our list of values up here. So at 0, we're going to be at 7. 1, 2, 3, 4, 5, 6, 7, way out here. So again, we're going to need, we know that we'll also go through the pole, I guess, at some point here, although it's not at one of these common values, but we can get it on there as well. So we'll just go and fill in a bunch of the other values here. This is a bit of a, time-consuming process, a bit tedious to compute all these values, but it is possible. I'm going to just cheat a little bit since I already computed these. At pi over 6, we're at 6.3. At pi over 3, we'll be at 4.5. At pi over 2, we'll be at 2. At 2 pi over 3, we're going to get negative 0.5. So we'll have to think about what happens when we're looking at negative radius values. We talked about that before, but we will be applying it here. 5 pi over 6, we're going to be at negative 2.3. At pi, we'll be at negative 3. So I know that's going to give us the top half of the grid on this shape. So let's just maybe stop there and connect the dots so far and see where we're at. So at pi over 6, we're going to be at 6.3. So that is about there. At pi over 3, we're going to be at 4.5. So I'm rotating to 4.3, and we'll go out 1, 2, 3, 4.5 is there. At pi over 2, we'll be at 2. So that is there. At 2 pi over 3, we're at negative 1/2. So we're looking at 2 pi over 3. Normally we would go out in the positive direction. I can get that a little cleaner. Come on, whoops. Normally we would be, oh, come on, quit moving on me. Going in this direction at 2 pi over 3, but since it's negative, we want to reverse back through, and we'll be looking, well, now it's zooming in on me, and it's not going to do this exactly, but we want to go right around there in the negative direction. So let me just erase that, and we'll be at 0.5 in the negative direction on 2 pi over 3. So it looks like we went to the wrong quadrant, but what this is doing is it's passing through the pole. So like I said, somewhere between pi over 2 and pi, we expected to go through the pole, and it did somewhere even between pi over 2 and 2 pi over 3. Let's just get the other values here. At 5 pi over 6, we're looking at negative 2.3. So again, we're looking at 5 pi over 6. We would typically go out 2.3, but now we're going to reverse it and go the other direction. And we're going to be getting a point right around there. The last one we'll get is pi, which is at negative 3. So if we're going out pi negative 3, then we'll reverse it and just go back the other direction there. So we're looking at negative 3. So far, what we've got is we're coming up, we're going through here, we're coming back down, we're going through the pole. Let me do that a little bit better. Going through the pole, hitting that point there, and then coming up like that. So here we're getting kind of this, almost kind of looks like an off-centered spiral so far. Let's see what we get with the rest of the values here. So if I plug in 7 pi over 6, we'll get negative 2.3. So we're getting some symmetry here. 4 pi over 3 is going to give us negative 0.5. 3 pi over 2 is going to give us positive 2. 5 pi over 3 is going to give us positive 4.5. 11 pi over 6 is going to give us 6.3. And then at 2 pi, we should be back to 7. So let's see how these look here. At 7 pi over 6, so that's going to be coming down this way, but we want to go negative 2.3. So that's going to be around there, or a little bit less than that, I guess. So it'll be around there. At 4 pi over 3, we want to go negative 5. So this is 4 pi over 3, but we want to go back the other direction at negative 5. At 3 pi over 2, we are at 2. So kind of just continuing this so far. We're making this inner loop, and we're going back through the pole, crossing it again there. So it looks like we only looked for one, but there should obviously be another one for cosine. For the unrestricted side of the cosine, we just found one of them there. So where am I at here? Now I need 11 pi over 6. That's going to be at 6.3, which is like around there. Oh, did I skip 5 pi over 3 is 4.5? 1, 2, 3, 4.5 is there. Or no, did I miss that one? I think that's what we want. So there is the rest of our shape. There, one of those is tripping me out, but maybe I'm just off a little bit. At 4 pi over 3, 5 pi over 3, 3 pi over 2, 4 pi over 3, 5 pi over 3, I want 4.5. 1, 2, 3, 4.5. Okay, there we go. I think maybe I was off a little bit on that one before. So there we go. So we are getting another Limaçon here, but here this has another inner loop on it. So we're going through the pole actually twice as we go through one full revolution from 0 to 2 pi radians. So let's take a look at the formulas here for these one-looped Limaçons. So again, same looking formulas, r equals a plus or minus b cosine of theta, r equals a plus or minus b sine of theta, but here the a value is smaller than the b value. And when that happens, we can actually find 0 values that will work. So we're going to go through the pole, and we're actually going to get this other inner loop in there. So here for all of these, we're saying a is less than b. And then again, all of the same kind of patterns apply, that for cosine, most of this, or the value farthest away from the pole, will be in the positive cosine direction, or in the positive x direction. If we have a negative b value, then it'll be in the negative direction on the x-axis, and same patterns for the sine, where the farthest value lives above or below if the b value is positive or negative. So there we go, we've got our one-loop Limaçons. Those are kind of like the big ones that we're going to be actually, there'll be some other ones. I take it back. There's just kind of this one in between before we get to the other main ones here. But these ones are called Lemniscates, or Lemniscates, depending on who you ask to pronounce it. And the formulas that produce this shape are given by r squared equals a squared cosine 2 theta, or r squared equals a squared sine 2 theta. And we get these kind of infinity-looking shapes here. So just notice that for the cosines, they either are left and right or up and down. So here we're seeing that the pattern isn't mostly living on the x-axis and mostly living on the y-axis. Here both cosines do that. And what we see for the sine versions is that they are kind of offset. They are not corresponding. At least this first point here should not be on the x-axis, because that's what cosine does. Cosine would give its farthest point there. So we're getting just these different offset shapes here for the Lemniscates. We don't see too much of that in our class here, but it is nice to just throw them in for completion. So we're not going to spend too much time looking at these, but I do want to spend a little bit of time looking at these rose curves. These are another big part, or another kind of super common polar curve here. So the formulas that produce these, so now there's no addition or subtraction here for the value that is in front, or being added onto these cosine or sine functions. They still have some stretch to them, some coefficient in front. But now what we're looking at is some value of n being in front of the theta value. So we don't want a to be equal to 0, or else we just get 0, and that's not very interesting. But each one of these loops here is going to be called a petal. So if n is even, then the curve will have 2 n petals. So what I'm looking at here is I see 1, 2, 3, 4, 5, 6, 7, 8. I see 8 petals. It looks like this has been a stretched a distance of 1, 2, 3, 4. So if I'm thinking about what this one is, this must be r equals 4 cosine of 4 theta. Since there are 8 petals, we know that if n is even, the curve will have double that number of petals. So if I count 8 petals, I can half that and get what the n must be, which is 4. Over on the other side, so if n is odd, then the curve just has n number of petals. So looking at this distance here, and this one is a sine value, so we see that the petal doesn't live on the x-axis. That's what cosines do. But here we're going to be offset a little bit for our first petal. It's going to be offset off of the x-axis. And here I think we're looking at r equals 4 sine of 3 theta. Since there's just 3 petals there, that's odd. We know that the coefficient in front of our theta will be exactly the same. So those are our formulas for rose curves. We're not going to do too much with graphing these by hand, but being able to recognize them right now is more our goal. So I just wanted to give you a few more examples here just to see what some different ones look like. Everything in the box above says exactly the same thing it did before. But here, all these have an a value of 5, just so that they all have the same general kind of size here. So we're looking at 4 theta for this cosine one. So again, the first petal lives on the x-axis. That's how cosine behaves. For this other one here, you can see it's slightly off for the sine. So that's when you're looking at Rose curves, the way to tell the difference between cosine and sine. Does the first petal live on the x-axis, or is it slightly off? So for cosine of 3 theta, we see that there's 3 petals here, and the first petal lives on the x-axis. So that would tell us that this is a cosine. And we see 3 petals here with the first petal off center, or off of the x-axis there, so slightly askew. So that tells us that this is the sine of 3 theta. So just wanted to point out some different looks of the shapes here to help get you familiar with them and be able to either look at the graph and get the general shape, or backwards, vice versa. So here is the summary again of all the different shapes. So just to kind of go through these one more time, a sine of theta, a cosine of theta is going to give us the circle that just kind of passes through the pole one time, or just intersects the pole. It's not centered on it, although we do have that version as well. We've got some cardioids, and so these next ones are all of the form a plus or minus b cosine theta, a plus or minus sine theta. All these say exactly the same thing. It just depends on the values of a and b. So here's saying a divided, so this is saying it in a bit of a different way than I did before, but a divided by b equals 1 means that a and b are exactly the same. That's when you get the cardioid. The one loop limnason is when, here it's saying that a divided by b is between 1 and 2. So this means that a is bigger than b, but less than 2b. So maybe I can write that on here. This says that a is bigger than b, but it's less than 2 times b. Or if a is less than b, then we get the inner loop limnason. So cardioid, a and b are equal. 1 loop if a is bigger than b. 2 loops if a is less than b. The lemniscates we barely went over here, but just to have them on here for completion. And then we looked at the Rose curves here. Here I can see that this has 1, 2, 3, 4, 5, 6, 7, 8 petals. The first petal is on the x-axis, so that tells me that this must be a cosine 4n. If I look closely, I could probably figure out that that a value is 3. So here I can see that there are 1, 2, 3, 4, 5 petals, which tells me that, and it's slightly off. This first petal does not start on the x-axis, and I can look at that petal. Looks like it's a distance of 3. So here this is looking like r3 sine of 5 theta. So just wanted to kind of unpack some of these here, these other examples, just so we can see them one more time. So there we go. There's our general summary. And I think with that, it is time to practice. So good luck with identifying these different shapes here. If you have questions, please let me know. I'm always happy to help. I'll see you in the next video.